Hey everyone, this is Dr. Walker. In this video, I'd like to go over the second example from v576, finding the magnetic field due to a current loop. In this problem, we have a current loop in the YZ plane. It's carrying a steady current, and we're trying to find the magnetic field along a point along the x-axis at a distance x from the center of the loop. So we know that we want to use the Biot-Savart law. Go ahead and write that down. There it is. And let's remember what are the steps to using this law. The first step is to draw ds, a length segment pointing in the direction of the current. So that has been drawn for us over here. And then the next thing is to draw the r hat vector, which points from ds to the point where we're trying to find the field. The distance r is the distance from ds to the point, and that has been labeled as well. So we know that we need to find a cross product ds cross r. Use your right hand rule, point your fingers to the left along the direction of ds, and then fold them towards you and see which way your thumb is pointing. Might be a little bit hard to see at an angle like this, but it's easier to see if you imagine that the point where we're trying to find a field is over here instead of over here. That way, when you have your fingers pointing to the left, then you can just fold them towards you because the x-axis is towards you, out of the page. And you'll see that your thumb points upward. But R points slightly down. So what you do is just angle your hand slightly down, and now you'll see that instead of your thumb pointing upward, your thumb is going to point at an angle here, like this, dB that is shown on this diagram. So what we have to do is make sure that the dBs from all the segments all point in the same direction before we can integrate. Now if we do the same thing with a length segment ds over here on the bottom, on the opposite side, then if you use the right hand rule, where you have your fingers pointing to the right and then you fold them towards you, but now you have to angle them upward a little bit because you have the distance r is going up a little bit, then you'll see that the dB is actually pointing in the opposite direction as the other one. So the dBs are definitely not all in the same direction. I encourage you to also try this with a length segment over here on the left side of the loop and one on the right side of the loop. If you use the right hand rule, you'll see that segment on the left side here will have a dB to the left in the positive z direction, and that the length segment over here will have a dB in the negative z direction. So I definitely encourage you to use your right hand rule to see that. So what do we do if all the dBs are not pointing in the same direction? We're going to see if there's any symmetry, if anything cancels out. Turns out that all of the left part, all the segments on the left part of the loop, all the z components that are positive will cancel out the z components that are negative from the right side of the loop. So there will not be a net z component for the field. We don't have to worry about it. Likewise, if we look at the fields that we drew over here, all of the upward y components here will be canceled out by all the downward components. So all of the upward part of the loop will cancel out the downward part of the loop as far as the y component of that field. So we will only have a field in the x direction. That's the only direction that we care about. So don't want to get ahead of myself, but the x direction is the direction that we care about. But before we get there, let's go ahead and write down an expression for dB just using one of the segments that we drew. So we have mu naught over 4 pi I, and then we need ds cross r. Well, what is the angle between ds and r? And you might think that it's theta, but it's not theta. Theta is the angle between the y-axis and the r hat vector. while ds here is along the z-axis for this one. So if you look at the fact that r hat is pointing in the x direction and ds is pointing in the z direction, you'll see that no matter where your ds is, it will always be perpendicular to r hat. So you can see right here, there is a 90-degree angle between ds and r hat. So the cross product is going to simplify to ds times 1 sine of 90, which is just ds. And then for r squared, let's go ahead and write that in terms of variables that we are given in the problem. And we're given that it has a radius a and it's a distance x. So let's write r in terms of a and x. And we can just use the Pythagorean theorem for that. We know that r is equal to the square root of a squared plus x squared. So r squared is going to be a squared plus x squared, since we're squaring that r. Okay, so we go ahead and obtain an expression for dB, and we can't integrate because all of the dBs are in different directions, but we realize we just need dBx. So I'm just going to find the magnitude of dBx. We already know the direction is along the x direction. Let's write an expression for dBx, mu naught over 4 pi I ds a squared plus x squared, so this is all dB, and then we need to find a certain component of dB. Well, with a little bit of trig, we can see that the angle here between the x-axis and dB is theta, is the same angle as the angle between the y-axis and r hat. It does take a little bit of trig, but you can see that we have a right triangle over here formed by x, a, and r. So we know that this angle here is 90 minus theta. And then we know that dB must be perpendicular to r hat since we used a cross product to get dB. So dB is perpendicular to ds and r hat. So if this is 90 and this is 90 minus theta, and we have a straight line, we know that this angle here is theta. So with that said, we know that dBx is going to be dB cosine theta because it's adjacent to the angle. It does require a little bit of work here. And now before we integrate, we do want everything to be written in terms of what we are given in the problem, which is a and x. So let's go ahead and write cosine of theta in terms of a and x. We know that cosine of theta is going to be equal to adjacent over hypotenuse, which is, if we look at this triangle again here, it's a over r. So we can go ahead and rewrite, I'll rewrite the whole expression, mu naught over 4 pi I ds a squared plus x squared, and then cosine theta is going to be a over r. R is square root of a squared plus x squared. So we can rewrite this one more time because we see that this is a squared plus x squared to the first power, and then a squared plus x squared to the 1/2 power. So we can simplify these two to make it a little bit neater. Mu naught over 4 pi I ds a over a squared plus x squared to the 3/2. Now we're ready to integrate. We know that the field Bx, just looking for the magnitude here, is equal to integral of dBx, which is the integral of this part here, mu naught I. And let's take out any variable that is constant. A is the radius of the loop, it's a constant. X is that constant distance at which we're finding the field. So the a is constant. The denominator, we have 4 pi a squared plus x squared to the 3/2. So luckily we can take all of these out of the integral, and we only need to integrate over ds. ds is that length segment here of the circle. And What I like to do is it's just a personal preference. I always like to write that arc length as RD theta, or in this case, since we've already used theta, we can say that the angle subtended by the arc length here is phi, or sorry, d phi, and so it would be r d phi, but the radius is a, so a d phi for ds. So we're going to write this so that I don't have to rewrite all of this again. I'm just going to rewrite this as a d phi, and the a will come out of the integral, but the integral we're going to integrate about the phi is going to go from 0 to 2 pi, doesn't matter where you define it from, it's going to be from 0 to 2 pi. All right, so we are almost ready. We have mu naught I, a times a here, a squared over 4 pi, a squared plus x squared to the 3/2. Then when we integrate d phi from 0 to 2 pi, we just get 2 pi for this integral here. And we can do one last simplification. We can cross out the pi's and cross out the 4 and make it a 2. So our answer for the field is mu naught I a squared over 2 times a squared plus x squared to the 3/2. Now the only thing I would like to do before I make this a final answer is simply because usually the radius of a loop is given as a capital R instead of a lowercase a, I want to go ahead and say that it's going to be r squared instead of a squared. So just make that lowercase a, make it a capital R, so that we can use our common symbol for the radius as an uppercase R. Okay, so this is the first part of the problem. The next video will have the other two parts.